You have to allow the. Yeah, I think we can start.
I forgot the introduction material.
Okay, yeah, okay.
Does anyone can see the screen?
Yes,
It's
I can
good.
see it.
Yes, it's good, Liang.
Yeah, I think, Jim, you want to introduce? Well, I left the material at home. It's not going to do me any good. I don't know where it is. Oh, I need the abstract. Okay, let me go for it.
Yeah.
You don't have a copy of the abstract?
Jim, I have it. Would you like me to announce?
Well, I
Introduce.
guess you're going to have to.
Okay, are we ready to go?
You're ready to go.
Yeah, okay.
Liang, just let me know when you're ready and I'll introduce.
Do have. Chad, I can do the introductions.
Okay, oh, okay, go ahead then, whenever you're ready. That's good.
Well, hello, everyone. Can you hear me okay, Chad?
Yeah, you're clear, Jim. Sounds good.
Okay, well, I'm James Freckles, the principal investigator of the Lehigh NHERI Experimental Facility. I want to welcome you to our seminar today as part of the NHERI Lehigh seminar series. We have a visitor, former Lehigh grad from Korea. His name is Professor Yunbyeong Chae. He's going to present today on a special topic that's close to his interest. And let me introduce you first a little bit about his background. As I mentioned, he's an associate professor. He's currently within the Department of Civil and Environmental Engineering at Seoul National University, that's in South Korea. And he's been there since September of 2021. I mentioned also he's a Ph.D. Or he's a Lehigh alum. He received his Ph.D. from Lehigh University in 2011 and got his MS and BS degrees from Seoul National University. And prior to joining Seoul National University, he was at Old Dominion University, that's in Norfolk, Virginia. Now, his research interests include many, but what he'll primarily focus on today is innovative resilient structural systems, structural control, performance-based design, and large-scale experimental studies. He also, aside from that, has interest in robotic motion control. And I'm happy to have him here today. His title of his presentation, as you can probably see on the screen, is Real-Time Testing for Investigation of Dynamic Response of Structures. So with that, I'd like to give the podium to Yunbyeong.
Thank you, Dr. Rickers. Good morning. My name is Yunbyeong Chae, and I'm standing here to present my research work. I'm very happy about that. And I remember that last time I was standing here was for my PhD defense almost 12 years ago. At the time, I was here to get evaluated for my PhD work. But now I'm standing here to share some of my research work. And I'm so happy about that. And I'd like to thank again Dr. Rickers for inviting me for this and then seminar series. Okay, today I'm going to talk about the real-time testing focused on real-time hybrid simulation and real-time cyclic loading test for investigating the dynamic response of a structure. I guess the many people now are quite familiar with the real-time hybrid simulation, but some people may not. So let me briefly talk about the concept of real-time hybrid simulation. In real-time hybrid simulation, we have analytical substructure and experimental substructures. So unlike the other shake table testing, we don't construct the entire structural system. We just manufacture and construct the structural component of our interest, and then test it in the lab. The remaining part of the structural systems modeled numerically. So here you can see change the other pointer here. Okay. So the equations of motion. Generally, we separate this restoring force term, like the restoring force coming from the analytical substructure and the restoring force coming from the experimental substructure. They are combined together, and then this equation of motion solved numerically to get the structural response at the next time step. As I said, because we only test the structural component of interest, which is generally small compared to the entire structural system, this real-time hybrid simulation is very cost-effective and it's good for conducting the large-scale testing. Okay, let me explain further about the real-time hybrid simulation using this figure. Here we have the two-story building structure with the dampers in the first and second story. Let's say that the damper has the highly nonlinear behavior, which is difficult to analytically model. And let's say that the remaining structural system is relatively easier to analytically model. Then in real-time hybrid simulation, this entire structural system is divided into two components: the analytical substructure that consists of the entire building structure except for the damper. And the damper can be tested in the lab using the hydraulic actuator system like that. Then we have the simulation coordinator combining these two substructure systems. It also has the actuator delay compensation and the numerical integrator. So we input the earthquake ground motion to simulation coordinator. Then it provides the command displacement to both substructures. Then the simulation coordinates collect the restoring force from each of these substructures. Then the equation of motion is solved numerically to get the structural response at the next time step. So if all of this procedure is conducted in real time, then we call this test as the real-time hybrid simulation. Otherwise, it is called the slow hybrid simulation, or sometimes just called hybrid simulation. Because we have the numerical substructure, analytical substructure, and the experimental substructure, they should be synchronized at the same time without any significant time delay during the simulation. In order to achieve that, it is very important to have the good actuator control that does not have any significant time delay. Of course, we need to have the good and stable integration algorithm, but physical-wise, it is very important to have a very accurate and no significant time delay displacement control algorithm. For that, we developed the actuator delay compensation algorithm, which is called the adaptive time series compensator. Of course, there are many existing displacement control algorithms for actuators, but most of them requires the system parameters that should be calibrated in advance. And those system parameters are quite different depending on the hydraulic system and test specimen. So it's a quite cumbersome work. And even if we believe that the optimal calibration of these system parameters in advance, but during the test, we cannot guarantee if those values are working well or not. So in order to resolve this issue, we developed this ATLSS compensator, which does not require the user-defined system parameters. Almost everything is calibrated automatically, optimally during the simulation. So we can achieve the better actuator delay compensation by using this compensator. Let me show you the performance of this ATS compensator. Here you can see the three different displacement time history. The black one is for the target displacement which we want to achieve by using the actuator. And the blue line shows the measured displacement without using any compensator. And the red line shows the measured displacement with using the ATS compensator. You cannot see any significant difference from this figure for this entire time history. But if you look at the close-up view of this area, then you can see the difference. Here, you see the target displacement. And if you don't use any compensator, you see the delayed response, which is about 21 milliseconds here. But if you use the ATS compensator, then you can see that the good match observed between the measured displacement with the ATS compensator and the target displacement. Someone may say that the 21 millisecond time delay here is really matter. Yes, the answer is yes. Depending on the complexity of the system, of the numerical, the entire system, this amount of the time delay can result in the inaccurate response as well as the stability issue. So we really need to resolve this kind of the time delay issue for the control of the actuator. Now I'm going to show some experimental test result for the real-time simulation and some real-time dynamic test. Here we have the three-story steel frame building with the two MR dampers in the first and second story. Sorry, as you can see here. That's the floor plan, and we have the moment resisting frame along the perimeter of this building. And inside of this building, we have this DBF, damped brace frame, where the MR dampers reside. In this simulation, we only considered the one quarter of this entire floor plan, assuming that the unidirectional earthquake ground motion and the symmetry of the building. So for the real-time hybrid simulation, the MRF here along the perimeter of this building and the gravity frame, they are analytically modeled. And the DBF and the MR damper in the first and second story, they are physically manufactured and tested in the lab, consisting of the experimental substructure. That shows the test setup for this test, real-time hybrid simulation. You can see the big frame here. This is not the test frame. They are just the reference frame to hold the test frame inside of this frame. You can see the test frame DBF inside of this giant big frame, the DBF, and the first floor, first story MR damper here and second story MR damper there. Okay, so you can see it like that. Okay, and each floor level we have a large capacity dynamic actuator connected. Three actuators, but it's the unidirectional one. Okay? And you can tell how big this test setup is by comparing the height of the person here. That's pretty big, although it's the 0.6 scale test setup. Okay. Let me show you the video we captured during the real-time hybrid simulation. You can see the actual movement of the frame and the MR damper from here. And you can see the motion of the MRF and the gravity frame, as well as the damper hysteresis for the first story and second story MR damper. And you can see the floor displacement from this window. Okay, let me start the video. Oops, oh, it doesn't work. Oh, sorry.
You have to get out of pointer mode. You have to get out.
Oh, really?
You have to get into pointer option. Go. So you have to unclick the laser pointer. There
Oh,
you
yeah.
go.
Okay. Thank you. All right. Okay, so the displacement was not so large and we didn't have any failure here. Some people probably expected kind of the collapse for after this test, but because we used the MR dampers here, the good energy dissipation we can achieve here so that the displacement was not so large. Okay, but anyway, we were able to achieve the successful real-time hybrid simulation result. And from this result, we were able to compare the performance of the semi-active control algorithm and the passive control case. So that's the result for the performance comparison. So without the damper case, no damper case, and the passive control, LQR, and the PAC, these two are for the semi-active control. But we are not able to see any significant difference between the passive control and the semi-active control after this test. Okay. So similar results were observed from the flow response spectrum for the top floor roof level. So if we don't use any damper, the black line here, then we have the large spectral acceleration, but with the MR damper, then we can have some reduced spectral acceleration. But again, we didn't see any significant difference between the passive control and the semi-active control. Okay, all right. That was the other test while I am the postdoc at Lehigh. And after that, I conducted some tests in Korea using the other test setup there. So this one is for the real-time hybrid simulation for two-span bridge. Okay, let me show you some of the feature for this test. All right, we conducted some hybrid simulation, real-time hybrid simulation and slow hybrid simulation for two-span bridge. And in this test, the bridge pier, reinforced concrete bridge pier in the middle, it was tested experimentally in the lab, and the remaining structural system, that is the superstructure of this building, it was analytically modeled using as the single degree freedom system. Okay. So that shows the test setup for this real-time hybrid simulation is pretty simple. Okay. We only use the one actuator controlling the horizontal displacement of the bridge. So that's the other actuator, and this shows the represent the bridge pier in the middle. Okay, its height is about 1.55 meter, and it has the square shape cross section. And so obviously, the bridge pier is subject to actual force, but at the time we didn't have any good control algorithm or knowledge for actual force control in real time. So we are not able to apply the actual force. So we just decided to apply the lateral displacement only. So that's why we use the single actuator like that. Okay, before we conduct the hybrid simulation, we conducted some slow cyclic loading test and the fast cyclic loading test with the different loading velocity. Because we were curious about the rate dependency of this kind of structural system. As we know, the squeak loading is real-time one and the dynamic one. But most of the existing tests in the lab we have conducted so far, it's very slow test, right? So I was curious why we should conduct the slow test rather than conducting the test in real time and the dynamic one. Yes, we conduct those tests using the Chae table, but if you use just the hydraulic actuator and just conduct the part of the structural system, the most of the existing study only conduct the slow test. So I was curious why we should do that, because it was not so natural for us. So in order to see any difference between the slow test and the real-time test, we conducted this kind of test with the same displacement history, but loading rate is different. The same displacement history for the slow test and the fast test. But if you, as you can see here, the time duration for the slow test and the fast test, they are quite different. So the maximum velocity for the fast test is 220 millimeter per sec. Slow test is 2.1 millimeter per sec. And this is the hysteresis loop after these two tests. The green line shows the result from the fast test, and it is, you can see that we have the larger hysteresis loop compared to the slow test. We can observe the increased strength, and also we can observe the enlarged the hysteresis loop that will increase the energy dissipation capacity. So basically, it tells us that the conducting the slow test will give us the conservative test result, which is safe. But please note that this is just the test without actual force applied to the column. Okay. Now, after this cyclic loading test, we conducted real-time and slow hybrid simulation to see if there's any significant difference depending on the loading rate. That shows the hysteresis loop after the slow and the real-time hybrid simulation. Slow is for red and blue is for the real-time hybrid simulation. Because of the increased strength with the fast loading rate, and also increase the energy dissipation, we obtained the reduced the displacement, as you can see here, when you conduct the real-time hybrid simulation. Okay? So that means also, if we conduct the real-time testing, then we probably have the conservative test result, which may be okay, but we cannot conclude that this is the general case, because this is just a test without actual load and just a test for the selected structural system. Okay. All right, this slide shows the damage pattern after the slow hybrid simulation and the real-time hybrid simulation. We conducted the 3 slow hybrid simulations, same test, and another 3 real-time hybrid simulation. And it shows the crack pattern after the slow test and the real-time test. Because the column was designed so strongly, we didn't have the significant damage, but we can still see some difference in the damage pattern or crack pattern. From the slow hybrid simulation, we can observe the 3 major cracks like that, here and here. But if we conduct the real-time hybrid simulation, we can only observe 2 major cracks at the bottom side. That means with the real-time testing, the damage can be concentrated at the base of the column. That can affect the strength, and most likely that can impact on the ductility and the posterior behavior of the structural system. So it suggests us to conduct the more real-time testing to get the better understanding for the earthquake response of the structural system. If we can do the real-time testing, why not? Why we need to do conduct only the slow testing? We can obtain the better structural response, more accurate response by conducting the real-time testing. Yeah. All right. After the test, as I said, we were only able to apply the horizontal force or displacement. Actual force was very difficult at the time to control. So we developed the new actual force control algorithm and conducted the new test with the actual force applied. Okay, so these 2 figures shows the one of the existing test for the steel beam column part and the reinforced concrete bridge pier. Because the actual force control was very difficult, these existing tests only conducted slowly to have a better control for the actual force or actual displacement. So at the time, it was very difficult to have a good accuracy in actual force control. So in order to resolve this kind of issue, we developed the new force control algorithm, which is called the DATS force control method. So the idea here is very simple. We just inserted the spring, compliance spring or linear spring between the actuator and test setup. So according to Hooke's law, as long as this spring inserted here behave linear elastic, then the spring force is proportional to the spring deformation. So if we can control the spring deformation accurately using the actuator here, then we can control the force applied to the test specimen. That's the other basic idea here. So by using the ATS compensator and using this compliance spring, well, we are able to achieve the good force control. So in order to validate this new force control algorithm, we constructed this simple test setup, single degree freedom test setup with a nonlinear MR damper. So here we have the steel mass and the linear spring here, coil spring, and the MR damper. So this part consists of the single degree freedom system. Because of the MR damper, the behavior of this system will show the nonlinear response. And on the left-hand side, you can see the actuator. And this is the compliance spring inserted between the actuator and the test setup. So again, by controlling the spring deformation here, we can control the force applied to this test specimen. Okay, that's the idea here. Let me show you the test result. We conducted the sine sweep test for the force. The top figure shows the target force that should be applied to the test setup. Also, it shows the measured or controlled force applied to the test setup. So the amplitude doesn't change during this sine sweep test, but the frequency changed. Okay. You can see that the very good agreement between the target and the measured force. That's the result we obtained using the new real-time force control. Okay. The second figure here shows the displacement of the test setup. I mean, this part, okay. The blue line that shows the displacement of the test setup, test structure. And the red line shows the displacement of the actuator. Of course, they should be different because we are controlling the spring deformation here, okay? And you can see the resonance behavior from this measured blue line displacement of the test structure. We have the maximum displacement response around this time, around this frequency actually here, about 1.6 hertz in this case. Okay. Please note that in the past, it was almost impossible and very difficult to control the force around the natural frequency of the system. But by using this new force control algorithm, we were successfully able to control the force around the natural frequency of the system. Yeah, that shows the superior performance of this real-time force control algorithm. So someone may say that if this kind of the performance level of the force control is really hard to achieve, someone may be curious about that. The answer is yes. If you use the existing method, it's very difficult to achieve this kind of level. Let me show you the result. If you use the existing force control method, like the PID controller, the same target force, but here the black line shows the measured force using the existing PID controller. So it's not even close. There's a lot of difference here. And also, if you look at the response at the end of the test, we saw the high frequency oscillation along with the very annoying noisy sound. Okay, so that means we have the limitation of increasing the P gain. So if we increase the P gain, we can achieve the aggressive response. Sometimes we can achieve the better response, but because of this high frequency oscillation, unstable response, we were not able to increase the P gain anymore. So that's the kind of the maximum, the best the achievement we can have with the existing PID controller. So you can observe the big difference here. And also you can see the superior performance of our newly developed the force control algorithm by looking at this result. Okay. All right, so that was the result by using the coil spring for the compliance spring between the actuator and the test setup. But we are also interested in applying this method for the large scale civil infrastructure system. And so in order to realize that kind of the large force application, we developed the new loading frame, which is called the flexible loading frame. As you can see here, it looks like the existing loading frame, okay? But the main difference between the existing and this new system is in this flexible loading frame, we allow the relatively larger bending deformation. When you apply the force, when you pull down the loading beam here at both ends using the actuator, then we can see this kind of the bending deformation. Okay? But as long as we design this frame to behave like a linear elastic under the given maximum force, then the bending deformation at the end here will be proportional to the applied force to the test specimen. In this case, in the middle. Okay. So basic idea is the controlling the bending deformation of this beam using the actuator installed at both ends of this loading beam. So existing loading beam has very steep, very large steepness, so it does not allow any visible deformation at all. But for this flexible loading beam, we allow some appreciable deformation. Okay. All right. So by using this flexible loading beam, we were able to apply the actual force during the real-time testing for the RC column given here. Here we have the RC column, and this is the flexible loading beam, and the two vertical actuators connected here. Basically, we pull down the loading beam at the end, and also we control the bending deformation, the deformation here of this loading beam using these actuators, which is proportional to the actual force applied to the column here in the middle. Okay. So we conducted some slow and fast or real-time cyclic loading test for this given displacement loading history. Okay, we gradually increase the displacement, lateral displacement of this test setup. And this figure shows the controlled actual force. We wanted to apply the constant actual force during the cyclic loading test. And that's the controlled or measured actual force for the fast cyclic loading test. Okay, where the maximum velocity is about 250 millimeter per sec. So it's almost constant, as you can see here. Target force is 144 kilonewton. Although we have some fluctuation here, but it's a small, less than 5% of 144 target force. Okay, and this is the case for slow cyclic loading test. You can see that it's almost perfect constant loading applied during this cyclic loading test by using this new force control algorithm and the flexible loading frame. Okay. All right. So this kind of the force control is very difficult to achieve in the existing test. That is the test conducted in the University of Colorado. Similar test setup as we had, but they have the difficulty in actual force control. That's the lateral displacement history for the slow test and for the fast cyclic test. And this shows the controlled force or measured actual force. The blue line here, that's the final measured actual force for the slow cyclic test and for fast cyclic test. You can see that the large error. It should be, it is supposed to be flat line, constant actual force, but you can see the large fluctuation here, even for the slow cyclic test. That clearly demonstrates the difficulty of controlling the actual force by using the existing force control method. Yeah. All right, this slide shows the hysteresis loop after we conducted the slow cyclic test. Okay, and we also conducted the fast cyclic test, and it is overlapped here, the red line here. So you can see that the reduced strength by conducting this fast cyclic loading test. But in the previous case I showed earlier in today's presentation, we observed the increased strength with the fast loading case. But for this case with the actual load, we have the reduced the strength with the real-time testing. So quite different. It depends on the structural system, I think. Also, it depends on the details for the layout of the rebars. But for this selected column system, we observed this reduced strength by conducting after the real-time testing. So it's about the 10 to 15% strength reduction, which can demonstrate the importance of testing the real-time testing. Okay. All right, that shows the damage pattern after slow test and the fast cyclic loading test. You can see that the distributed damage pattern after the slow test, but with the real-time test, fast test, we see this concentrated damage pattern, which resulted in the reduced strength in this case. Okay. So it should be noted that with the slow test, we have the distributed damage, but with the fast loading test, we have this concentrated damage, which can impact on the strength as well as the ductility. We may even have the earlier failure when you apply the real-time loading. So I believe that it is very important to conduct the real-time testing. All right. We also conducted the real-time hybrid simulation with the same test setup. But this case, we applied the horizontal ground motion as well as the vertical ground motion, which is considered to be very challenging in the existing study. Okay, but with this new force control algorithm, we were able to successfully conduct this challenging testing subjected to both the horizontal ground motion and the vertical ground motion. Okay. So this shows the test result. The one here shows the lateral displacement comparing the target displacement and the measured displacement of the bridge pier column. So we can see that the good tracking of the measured displacement following this target displacement, the displacement control. And this shows the actual force applied to the bridge pier as column. Because we applied the vertical ground motion, the actual force is no more, it's not the constant anymore. So depending on the vibration of the bridge deck, as well as the vertical ground acceleration, we have this kind of the fluctuation of the actual force. Okay, so you can see that the good agreement between the target actual force and the measured actual force. The close-up view here is showing here. Then you see that the good tracking of the measured actual force, which can show the potential of the newly developed the actual force control and the newly developed real-time hybrid simulation concept for the structure subject to both the horizontal and vertical ground motion. All right. So we also conducted another column test subject to both the lateral force and the axial force. So that's the video showing this test. Here, this is the new flexible loading frame, of which capacity is about the 800 kilonewton. In the previous test, the loading capacity was only 180 kilonewton, but we increased the capacity of the loading frame to up to the 800 kilonewton. So let me show you the some cyclic loading test, real-time cyclic loading test for this column. We apply the natural force. Okay, let me stop the video here. So you can see the some banding deformation here compared to this reference frame. Okay, if I go back this test setup to the original state, then you see that the banding deformation between these two. Okay, so you can see the deformation visibly by pulling. We pull down the beam here and there. Okay, then that banding deformation is maintained throughout the cyclic loading test. Yeah, with the increase of the deformation, you will be able to see the damage of the column at the bottom here. Yeah. Yeah. Okay. Then the frame will go back to its original position to release the actual force to the test setup. Yeah. Okay. That's how the flexible loading frame works. It's simple again. We just control the banding deformation of this flexible loading frame, and it is controlled to be constant. The banding deformation is okay. It's not the actuator displacement. So banding deformation is controlled to be constant during the cyclic loading test. Sorry. Okay. We also conducted another test using the flexible loading frame. This is for the test setup of the reinforced concrete shear wall of the nuclear power plant structure. That's the test specimen, RC shear wall. And it is subject to the in-plane deformation as well as the out-of-plane deformation. We also apply the actual force, this shear wall, using these two large capacity vertical actuators connected to the flexible loading frame here. This flexible loading frame was designed to have the force capacity up to 1,200 kilonewton. Okay. We actually applied the 1,100 kilonewton during the test. Okay. And this kind of test was very challenging in the existing study because it was difficult to construct the test setup like that. And also it is difficult to apply the actual force when the in-plane and out-of-plane motion applied at the same time. But by using the flexible loading frame and the newly developed force control algorithm, we are able to successfully conduct this test. Okay. That's the result of the actual force control. We conducted the unidirectional test and also bidirectional test. Unidirectional means the in-plane deformation applied only, and bidirectional, the in-plane and out-of-plane motion applied at the same time. And during this lateral deformation, the actual force is supposed to be applied constantly. Okay. So we conducted 5 different tests and with a different actual force. First case is the 550 kilonewton actual force, but unidirectional one. The purple line shows the controlled actual force. It's almost same as the target force here. Okay? And this one shows the result from the unidirectional as well as the bidirectional loading test with a different loading pattern. The black line shows the unidirectional case with 1100 kilonewton actual force, almost constant, okay, which is good. The remaining part shows the actual force during controlled during the bidirectional test with a different loading pattern. We have some kind of this kind of the fluctuation of the force because we didn't consider the velocity feedback for this test for the actual force control. We had this kind of the fluctuation, but if we consider the velocity feedback, then definitely we would be able to the better actual force control. But overall, we were able to achieve the successful, satisfactory control of the actual force. All right, that shows the damage pattern after that test. The typical shear failure, and the wall was designed to have the shear failure. Okay? So we have this kind of damage after the test. And this shows the summary of the test result. As I said, we conducted the unidirectional and the bidirectional test, and we are interested in seeing the effect of the actual force and also the effect of the bidirectional loading compared to the unidirectional loading only. The left-hand side figure shows the effect of the actual force. The low actual force case, 550 kilonewton with 4.5% actual force ratio. And this black line shows the case with a high actual force, 9% actual force ratio. Okay? You see that the increased strength, but we have the reduced ductility. That means the earlier failure of the wall is observed with a larger actual force. Okay? We had the increased strength, but earlier failure observed with large actual force. And the figure on the right-hand side shows the case between the unidirectional loading and the bidirectional loading. Unidirectional case here, the black line, same as this one. And these are the result from the bidirectional loading with the different loading patterns. So we can see that the strength here, initial stiffness, we do not have any significant difference between in the initial stiffness between the unidirectional and the bidirectional one. However, there's the strength reduction as well as we have the early failure of the system if we have the bidirectional loading applied to the wall system. Okay? So that means the importance of the three-dimensional testing to evaluate accurately the seismic performance of the reinforced concrete shear wall, because the earthquake loading is three-dimensional, then we definitely need to consider the three-dimensional loading. Okay. We also conducted the hybrid simulation with the same test setup to obtain the experimental flow response spectrum. Okay. The FRS, flow response spectrum, this is related to the design of the mechanical equipment inside of the nuclear power plant structure. But since the nuclear power plant structure is large and massive, it is very difficult to obtain the experimental flow response spectrum. Okay? So far, FRS was obtained only by using the numerical simulation, finite element analysis. But if you use the hybrid simulation, we can obtain the experimental flow response spectra. That's the typical nuclear power plant structure. We modeled the system, shear wall system here using this structural model. And the first story was tested in the lab using the test setup here, because when you have the strong earthquake, the damage will be concentrated in the first story. So the second and third story, they will pretty much remain linear elastic. Okay, but we modeled this part using the tri-linear model. Okay, and the first story shear wall is experimentally tested using this test setup. And this shows the experimentally obtained flow response spectrum with a different intensity of the earthquake ground motion. As far as we know, this is the world first experimental flow response spectra, okay, obtained experimentally. Okay, in the past, again, only the numerical simulation was available. So, but by using the hybrid simulation, we can obtain this kind of the flow response spectrum. All right, that's it for my today's presentation. It's mostly related to the real-time dynamic testing. So, okay, if you have any question, I would be very happy to answer your question, whatever it is. Okay.
Anyone have questions, can leave your questions on the Q&A sections.
Yeah.
I have a question.
Okay, yeah.
You know, the compliance there, it's going to also be influenced by the compliance of the test specimen itself, especially axially. So these specimens are very rigid, if you wish, very low compliance. What happens if you have ones that basically more coupling, that is, there's more compliance in the test specimen than that? The actual force, you know, it's still probably be more challenging because the deformation that's in the spring will develop a force, but it's going to also rely on the deformation of the specimen that's more or less either in series or in parallel, right?
Exactly, yes, right. That's why we, for this test setup, we installed the ability here to measure the displacement of this test setup. It is considered in the force control for the control of this deformation of the compound string. Yes.
Right. You want to have feedback on the
exactly.
Yes, of course. This I guess wouldn't matter too much if the spring here was nonlinear. It would still work as long as you use feedback from, in this case, your LAT on the right side.
Exactly. Yeah. We also needed to, in order to achieve the better performance, the velocity feedback should be included in this algorithm. And for this test, the velocity feedback was used so that we were able to achieve this kind of the good force control.
So when you did that though in the ATS, you feedback the displacement, but you still consider the numerical.
Yes, right, exactly.
Right, second and third, terms there.
Yeah, exactly.
When you did these tests, did you ignore that velocity and acceleration? Did you say you ignore the velocity effect, or did you?
Okay, that's a good question. So for it is very important to consider the velocity of this compliance spring. Then we needed to, we needed to know the velocity of this actuator, which can be obtained from the time differentiation of the target displacement. That's the given in advance actually. So we can achieve the smooth target velocity. However, it is difficult to achieve the smooth velocity feedback for the test setup. What we did for that part is that we measured the acceleration of this test setup. We installed the accelerometer as well, then integrated the acceleration data. Then it is combined with the time differentiation of the LBDT displacement, which was filtered out. There's the actually time delay. But that time delay was compensated by using the integration of the acceleration data. It's a little bit complex, but by using these two, we are able to achieve the smooth velocity feedback of this test setup.
So when you have the compensated signals, not necessarily displacement, it's velocity. So you dot C rather than use.
Yes, exactly. Actually, the displacement is also important. Yeah, both the displacement and the velocity. So if you use the velocity feedback, then for this column test, we didn't use any velocity feedback at all, actually. That's why we have this kind of a fluctuation, actually.
But I think the challenge though is if
Yeah.
you try to, you have a choice, either displacement or velocity, because both are related through time.
Yes.
If you decide you're going to compensate a velocity, you're more or less stuck with opposing displacements over a certain ramp,
Mhm.
right? Period. Whereas if you control the displacements, then the velocity is a result of that. Just like
Yeah.
you control the velocity, the displacement is a result of that. So
Yeah.
you have to decide whether it's u dot or u sub c, I guess. And you think u sub c dot, the velocity is better than the displacement.
Yes, right, exactly. Yeah. And also we are working on developing the new force control algorithm because it requires, this force control algorithm requires the velocity feedback for better performance. But it always, we need to have some kind of velocity sensor for that. But I was not able to find any good velocity sensor for that. So that's why we use the accelerometer. But this kind of, we need to have more channel accelerometer sensor and the channel, and we need to have some kind of process of the data with that. But we are working on the new force control algorithm that can be obtained directly from the force feedback and the displacement feedback. So working on that, and hopefully we can see some result this fall semester. Yeah.
Yeah, that's interesting. So if you use the accelerometers,
Mhm.
you know, I think one of the challenges that we've observed is when you have an actuator attached to the specimen, you have an accelerometer, it senses the hydraulic noise.
Yes, exactly.
Right, so
Yes.
you're going to get noise in accelerometer. So I guess you're going to have to filter that out, which introduces a delay.
Yeah, but that usually the kind of the noise from the actuator, it is usually related to the oil column resonance frequency,
Right.
around the 20 hertz or a little bit less than that or higher than that. But the frequency response for this kind of test setup or most civil infrastructure is kind of the low frequency, less than 10 hertz. So 20 hertz fluctuation and the acceleration frequency content that can be canceled out if we integrate the acceleration data to obtain the velocity. Then its effect is very small, actually.
I see.
Yeah.
It's space somewhere.
Yeah.
Okay.
Yeah. Right. Yeah.
Okay. Yeah, very interesting. Sorry, I didn't mean to dominate the questions there, but no one else was asking, so I thought I would ask.
But that's the other very core part of this algorithm, actually. Yeah.
So the interesting thing that came to mind when I was looking at this, I'm just thinking about friction pendulum bearings, whatever.
Yeah.
Does it kind of imply that there's a vertical force in the bridge seem to have an effect?
Yeah.
If you're isolating that structure, that's going to affect the gravity loading on the structure and the acceleration of volume. It seems like the friction pendulum bearing need to consider vertical acceleration in the system.
Exactly.
As well as a translation, otherwise you don't get the right.
Yeah. So for such an isolation system, it is sensitive to the actual force applied to the bearing system. So that will definitely impact on the lateral response in the end. So for such a test, it is very important to have the actual force control in order to get the accurate test result.
Yeah, very interesting.
Yeah. So, but by using this method, I believe that we can conduct that kind of test, and also I'm planning on doing that kind of test later this year and the next year.
Yeah, I think you have some very good points. That I mean, I think maybe a lesson learned to perhaps the audience is that when you walk away from this, it's not just multi-directional, but it's 3D motion.
Right, exactly.
Is important, right? Not just unidirectional motion there.
Yes. Yeah.
Okay.
I always have a general question. So say you have ATS, but there's tons of compensator, right? Like sliding mode. So what's the benefits comparing your ATS with others? Like what people should use in the ATS?
Okay. Yeah, that's also a good question. So in the lab, we have many labs in the US and all over the world, right? And they have a different hydraulic system and capacity. And also for the test specimen, sometimes we use the small test specimen and the large scale specimen as we do at Lehigh. Okay. The existing compensator, they have the system parameters. They should be properly calibrated in advance before the test. Okay? But the calibration of this kind of parameter is difficult sometimes. And sometimes if we handle the fragile specimen like the concrete, and during the test, during the nonlinear behavior of the test specimen, the system parameters for the existing compensator, they should be changed to get the better test region. And sometimes the hydraulic actuator system, if you have the large velocity and the large displacement, the system parameters should be also recalibrated during the test. But most of the existing compensators, they don't have this kind of capability, okay? That's why we developed this kind of the ATS compensator, and the ATS compensator can resolve this issue during the test automatically and optimally based on the feedback and using the least squares method. Yes, right. That's the other major difference, I believe.
So,
yeah.
so Yunbyeong, I don't know, there's only 3 other participants. I don't know if there's any other questions. I have another question.
Yeah, okay, yeah. Mhm.
Does anyone have any other questions at all? I'm sort of moderating here, but it's okay if Yunbyeong asks if you have any questions. Do you have any questions at all, sir? Any other questions? If not, I have a question about ATS using the acceleration. Have you thought about what's called the jerk, which is a third order derivative? So it would make the bandwidth of that transfer function longer. Some of the challenges we usually face is these compensators in the transfer function then start to amplify because it's sort of an improper function, start to amplify at the higher frequencies. And if that higher frequency is too close to a structural frequency or a natural frequency in the system, you can have difficulties. If you looked into using a higher order derivative to try to lengthen the bandwidth there?
Oh yeah, that's also a good question. So if we can, I mean, theoretically, it is possible, but experimentally, I never tried that yet because my frequency range for my interest is typically less than 10 hertz. Okay, but if there's yet any application for high frequency response is important, then definitely we need to consider the third order or higher order term in the ATS compensator. But at the same time, I still believe that we gotta be careful about achieving those high order term because in ATS compensator we are using the low pass filter to achieve the velocity and the acceleration response. But if you use the low pass filter, then high frequency term is definitely, I mean, cancel down, right? Yeah, they decay down, right? So high frequency term is not considered basically if you use the low pass filter, but we can increase the cutoff frequency, of course, but then it will increase the noise level as well.
Right.
Yeah, there's always trade-off, I believe. Yeah,
exactly.
Yeah, so may not be so easy, may not be easy to control the high frequency oscillation. Its amplitude is also very small, right?
Yeah, that generates some thoughts there.
Yeah. Okay.
Okay.
Okay, there's no other question. We should close the seminar. Thank everybody for coming to this
Yeah,
seminar.
so I guess, I don't know if anyone's still on, but if there are, I want to thank everyone for attending the meeting today. And, thank you, Yunbyeong.
Thank you.
Yeah.